What do you need this for? So you need this for the MCMC methods, and there are many MCMC methods. This is like a big family of methods, and they're an active area of research. People are developing, better methods all the time. So I'll mention just two methods here, which are like the kind of the basic building blocks that I think are the most important ones. The first one is called Gibbs sampling. And the rule how you do this is that you sample each parameter in turn, one by one, from its full conditional distribution, conditional on the present values of all the other parameters, and you just go on. Like in our example, you sample A from the distribution, full conditional distribution, given the data and all other parameters. Then you change the value of A. Then you sample B, conditional on all the other parameters, then C, then D, then actually all the true locations. You sample them also from their full conditionals. After you have done that all for all the parameters, then you move on to the next step. You sample again A, then B, then C, and so on. So this is called the Gibbs sampling. And I draw this graph just a minute ago, where again, let's assume that we have, to illustrate that we have only a single parameter, so that I don't need to draw a 15-dimensional graph. MCMC goes so that this is like the iteration round of sampling. Like 1 means that we are looking at theta 1, 2 means that we look at theta 2, and so on. So it might look something like this. And then I said that after this transient, you converge to a stationary distribution. Okay, one of you was asking that if you just write down, let's say, a random walk algorithm, you don't necessarily assume that you stay in any given region. So why is this happening? It's happening because we defined the Markov chain, this process. We construct it in some special way, some kind of clever way. In this case, following this rule. Okay? If you do that, then there is a mathematical theory saying that what comes out as this stationary distribution of the chain is exactly that posterior distribution. It's actually an easy derivation. It's not many lines of derivation to show that that's the case, that the stationary distribution of that Markov chain is exactly the posterior. Okay. So this is one way to construct your posterior, get the sample from that.
But how do you start at the beginning when you start sampling the one? What are the values of the other?
Yeah,
exactly. You need to assume something.
Yeah, you have to assume some initial condition, and in a sense it doesn't matter because this mathematical theorem I mentioned, it says that the stationary state of this chain is the posterior distribution. Okay, stationary state is what you eventually get when you run this long enough. So wherever you start, you can start from any random location. You will converge to the same distribution. So in that sense, it doesn't matter at all. But it can matter in practice because, of course, if you start from far away, it takes more time to get to the stationary state.
That's the reason you need to have the priors, to give a good starting point and the limits of the range, no? Otherwise, you could have started any point in terms of values.
Well, I mean, often the starting point doesn't matter so much because if you are way off, you often very quickly go to the right parameter regime, like I will show in an example. But the initial value of the chain, that's different from the prior. It's not the same thing as the prior because prior is part of your model. Okay? After you have defined the prior and then the likelihood, after you have drawn this DAC and defined all the priors, everything is set. So then the posterior is well defined. There's only one posterior that will come out, whatever method you will apply. So all these methods that I talk about, they return exactly the same answer. Okay? For example, whatever is the initial condition. So in this sense, these are not important. There's no biology here. It's just a method to get the answer. Okay. And that's why it's really important to separate that from the model. Often if you read the literature, I mean, sometimes you just see this MCMC method, not the definition of the model. I think it's a bad way to write the paper, because it's really the model that's of interest for a biologist. MCMC is just a technical tool to get the answer.
So this lack of dependence on the initial condition, you mean the selection of the full conditional, which parameter are you doing to do the full conditional first, second, and so on?
Oh, okay. So we have this theta is a vector of these values A, B, C, D, and Z, and then Z is like Z1, Z2, until how many data points we have. So when you start doing this skip sampling, you have to give an initial value for all of these. You cannot figure out what's the full conditional probability distribution of A given all the rest if you don't know the values of all the rest. So you have to give values for all of those. But as said, the initial values, they don't matter, because eventually you converge to the stationary state. I think you were asking, like, in which order should you update these? Again, it doesn't matter. You get the same answer in the end, whichever order you do. That's part of this theorem. Okay? You can even do it in random order. You can do it in systematic order, random order. You can update A 5 times and then B twice and then A 3 times and then the rest once. You can do it in any combination. So it doesn't matter. You get the same. I mean, it matters in the sense that you might get the right answer faster if you do it in a clever way. But in theory, it doesn't matter. You will always get exactly the same answer.
But A to D are not updated. They remain the same.
Sorry?
A, B, C, and D are not updated.
They are updated. These are the parameters that you are estimating. Like, these are the parameters of the Weibull distribution. When you see the data, of course, you don't know exactly what are the right parameters. This is exactly what you are trying to estimate. Yeah. So they are updated. I think you had a question as well.
If you have more than one parameter, like you have a lot of parameters here, it's not. Is the process done like recursively or nested, or is it first finished with A, and then you go and do the same thing with B?
Yeah.
I mean, or while you are calculating A, you are also for the first parameter of A, you are now looking for the full conditional of B, and for the first of B, you're now nested in some way.
Yeah, you cannot do it in that way that let's first work out A and then move to the next one. You have to work it out in this way, that you work out you kind of update the full parameter vector theta in some way. This is now the value of theta in iteration around 1. And from that you get the value of theta in iteration around 2. And when you do this one step in this graph, you have updated all the parameters here. Okay? But this thing is saying you that you can do this, you can take this one step, this is the step of your Markov chain, in such a way that you go through these in any order you like, and then you update each of those conditional on the values of the other. After you have done the whole thing, like the whole vector, only then you record what is the value of this vector now, you store it, and then you move to the next step.
But you said that you could update the same parameter several times without updating the other parameters, so that's not considered a step. Right?
Yeah, it's considered a full step only after you have done you decide in which order you want to do these, systematic or random or some more times than others. You decide that yourself. But after you have done all of that, then you have taken one step.
How do you know when you have converged?
Let's come back to that later. Okay, this is the skip sampling. This is the simplest algorithm that you have, which is kind of nice because it's so easy in some sense. But it's often difficult to do in practice because it might be difficult to sample from this full conditional distribution. I mean, we can write down the expression for the full conditional as we did for this parameter B, but again, it might not be any standard distribution. So it might be that we can't sample from it. Okay? So that's why this is often difficult to apply as such in practice. So what I want to next talk about is another MCMC method. which also has the same property that, you know, if you apply that, you are guaranteed to converge to the posterior distribution. Okay, but this method is really general. You can apply that basically to any problem. So this is called the Metropolis-Hastings algorithm, and it's kind of utilizing the idea of Gibbs sampling in the background, so that again here you update each parameter in turn, conditional on the values of the other parameters. But if you cannot sample that parameter directly from the full conditional, you can follow this recipe. So you propose a new value for that parameter. I now call the parameter theta. So the new value I call theta hat from some proposal distribution. So you just make up a distribution by yourself. You can define this, construct this in any way you like. This Q theta is a proposal distribution from which you somehow randomize what you think could be the new value. Okay? I denote the density of this distribution Q by small letter q. So this is the density in terms of the new value theta hat. It might depend on the old value theta, the current value theta. As I indicate here, this distribution capital Q can depend on the present value of the parameter. I'll illustrate that in more concretely what it means in practice soon. Okay, so in some way you propose a new value, but you didn't sample it from the full conditional as you should have done. So it's not guaranteed that this is kind of a good value. So then there's an acceptance rejection step. So you decide by some rule, which is written down here, whether you accept this new value that you proposed or not. Okay? If you accept the new value, then you change the value of that parameter to the new value. If you don't accept the new value, then you just keep the old value of the parameter. Okay?
Then the order method, huh?
Yeah?
The order of the parameters matters.
Well, the order of the parameters doesn't matter again in the sense that you always get the same answer in the end. But it might matter on how effective this method is to how fast you get the right answer. Okay. If it happens that you don't accept the new value, then you just keep the old value. You don't propose again, you don't propose until you accept something, but you just keep the old value and then move to the next parameter. And this is the probability by which the proposed value Q hat, which you sample from that distribution, is accepted. So this A is the probability by which you accept the new value. So first you figure out what is this quantity here. It's just a number. Okay? And then you randomize based on that number if you accept or not. Sometimes this number can be bigger than 1. So then it's not the probability. That's why I write here minimum of 1 and A to make it technically correct. Okay? Let's then look at what is this probability A here. Well, it's the ratio of the likelihoods at the new value compared to the old value. Okay? So this is saying that if the new value is better in a sense that it's more likely, it gives a higher likelihood than the old value, then you should be more likely to accept it. Okay? So you are kind of climbing up this likelihood surface. If you propose a better value, then you accept it. But sometimes you also go down. I mean, this is different from maximum likelihood in the sense that you don't just search where the peak is, but you sometimes accept a lower value. Then what we have here is something that depends on the proposal distribution. So this is something that you can think of as a correction factor, because you can use any proposal distribution you like. It can create some sort of bias. You can, for example, decide that I'm very likely to propose some kind of values. And if you forget about that, then you too often you sample those kind of values. That's why you have to correct for it. So what we have here is the density of that proposal distribution going from the new value to the old value divided from going from the present value to the new value. Okay, and this choice here, it's not, again, it's not like an arbitrary choice. You can show using with a pretty simple calculation, I mean not entirely trivial but still nothing too deep, is that if you follow this rule, again you will converge to the stationary state, which is exactly the posterior density that you like to sample.
Can you explain again the last term in the expression? I understand the denominator. What is the numerator?
Here.
Yes.
So you are basically comparing, I mean that you are you start from the present value theta and then you propose this new value theta hat. Okay? And so you are kind of comparing that how often would you, if you start from here, how often would you propose that value compared to if you would start from here, how often would you propose exactly that value?
So it's two different densities.
Yeah, it's the density of the same proposal distribution, but it's evaluated either from here to there or from here to there. You compare these two.
Oh, same distribution, different positions.
Yeah. It's the probability of proposing the new value from the old value or vice versa. Okay, so this is the general case. This is the same formula I've written here on the yellow color. And let's now talk about some special cases of this general case. Let's start actually from the case of the symmetric proposal, because this relates to the question you are asking. So this is often the case that this proposal distribution is symmetric. Okay? Let's say that the new value is like normally distributed around the present value with some variance. That's one way to propose new values. This is symmetric. Then it's exactly the same probability of jumping from here to there than vice versa. So these two densities are the same. If that's the case, then this part cancels out and you simply have the ratio of the likelihoods. Then we have something which is called the random walk metropolis hastings. And one definition for this is such that the expected value of what you are going to propose is the present value. Okay? For example, if the new value that you are going to propose is normally distributed around the present value, okay, then the expected value is the present value. So you are kind of proposing a jump from the present value to some direction. That's why you could call this a random walk algorithm. So it's a random walk metropolis hastings. This is something that we often use, but it's not the only case. The kind of the opposite part of the continuum is that of the independent proposal. If you are using an independent proposal, then this proposal distribution does not depend in any way on the present value. So let's say that independently of what is the current value of this parameter, I always propose the new value from a normal distribution with mean 0 and standard deviation 5. This is also a valid proposal. I don't need to care what is the value of the present value of the parameter distribution. So in that case, this q theta actually doesn't depend on theta. Okay? In which case, you still have the same expression, but this, of course, also this density here doesn't depend on the current current values. So this is called independent proposal. Let's see, just for fun, what happens if you would use the posterior density as the proposal distribution. I mean, of course, you don't know what is the posterior density. That's the whole point why we are doing this sampling. But if you would know it, let's just see what this algorithm is doing. So in this case, the proposal density, q of theta, would be independent of the present value because you always propose from this posterior. So it's simply this posterior probability of theta given y. So instead of this q theta, I just substitute this expression there. And you see what happens. Things just cancel out. This gives 1, which means that you always accept. If you can sample directly from the posterior distribution, then you just always accept what you sample from there. Then trivially what you get is the posterior distribution. Okay? This silly derivation actually has some practical meaning, because it is kind of saying that if you are using an independent proposal distribution, then the best thing you can do is to use the posterior. Okay? You don't know that, but sometimes you can guess like a good approximation for it. You can guess how it probably looks like. And if you use that as the proposal, then you have a high acceptance ratio and you don't lose much computational power. So if you are using an independent proposal, then the kind of the algorithm is the better, the higher proportion of the proposals you accept. But that's actually not true with the random walk, as I will show in more detail. This random walk metropolis hastings, I think that's the most practical algorithm. That's what you most often use.
Can you explain, sorry, can you explain again the difference between the random walk and the symmetric?
No, there's no difference between these. You can very well have a random walk metropolis hastings with a symmetric proposal. That's actually the most common case. So you can think that this is a special case of that. Okay, what you have survived through this far has been kind of quite heavy theory. I mean, if you take a book by, for example, this Gell-Mann book of Bayesian data analysis, you have to read like at least the first 100 pages to get this far. So if you didn't exactly understand everything, shouldn't be worried that there is anything wrong with your brain. You just need to go through this a couple of times and then it becomes more clear. But from now on, everything should be simpler in the rest of this talk, because I'll go like in practice through what we have been doing. So now it becomes more similar to what you did in the computer exercises. And to do that, I want to simplify, just to make a simpler, like a toy example, by assuming this model with no observation error. So now our parameters are A, B, C. There are no other parameters because now the true location is not hidden. That's actually now our data. So I basically do here all the steps that you did in the exercise, but I'm not using R, I'm not using this package which does the MCMC for you, but I'm writing the MCMC algorithm myself, so that you can, if you want later, you can go through those slides and see how, in this case, random walk metropolis hastings algorithm, how it looks like. First I simulate data, and to do that I have to decide about the parameter values. These are like the true values of the parameters. I call them capital T pairs. Capital T means like the true values. Now these parameters of the model A, B, C, they all need to be positive parameters, because otherwise those distributions are not well defined. And this is a slight technical problem in the sense that it's easier to write, for example, this MCMC algorithm if you can allow any values for the parameters. So it would be much nicer if they could have any real values, not just positive values. That's why I don't actually work with the parameters A, B, C, but I log transform them. So my parameters are log A, log B, and log C. Because these parameters, they have to be positive. Okay. Like the parameters of the Weibull distributions, they have to be positive. And it's a bit more difficult to do these MCMC algorithms for parameters which are restricted to be positive or between 0 and 1 or whatever. It's much easier to do it if they can get any values. Basically because the random walk can go anywhere. So if I, instead of the original parameters, I log transform them, then they are any values between minus infinity and infinity are possible. Okay? So in this case, I just decided that my parameters A, B, C are 1, 2, and 4, but I log transformed them to get those parameters that I actually work with in the model. Okay? This is a and this is something that you have seen already. This is what I did yesterday. This is exactly the same algorithm for simulating correlated random walk model with Weibull distribution for step length and von Mises distribution for turning angles. If you see what's inside here for the parameters of those distributions, I have here the exponential of the true parameters 1, exponential of the second component of the true parameters, and so on, because I have to remember that those were not the original parameters but the log transform parameters I have to transform back. So this is how we simulate data, and this you can do already. Next we have to write down the expressions for all those components that I was talking about, the likelihood of the data and the prior. So this is my expression for the P y theta, the likelihood of the data given the parameters. Okay? In this case, this is the log likelihood of the data. So it's simply the logarithm of this expression, just for the sake that it's easier to work with the logarithms than the densities itself, but it's the same thing. And here TA, that's my data, like the table of data, and parameters is the vector of all parameters. Okay? So if you see what's happening inside this module, which is like a building block of like a function in Mathematica, is that I work out from the locations, I work out the displacements. So I just take the differences of the location vector. Then I figure out the step lengths. I calculate the length of each displacement. Then I figure out the directions of the displacements. I calculate the angle to which you are going in each displacement. That's not the turning angle, that's the absolute direction. Heading. Then I figure out the turning angle alpha by taking the differences of those headings. Then as Luca was explaining, you might get values which are not between minus pi and pi, or however you want to, define your distributions. I'm using it going from minus pi to pi. So if I go outside minus pi range, then I just add 2 pi or subtract 2 pi to get to that range by this expression. And then I can figure out the likelihood of the data. So what we have here is the probability density function. This is the probability density of this Weibull distribution with those parameters that we feed in, given evaluated at the step lengths. So step length is now a vector. I had like 100 steps in my data. There are hundreds values of L. I just evaluate the value of this, the probability density of this distribution for each of those. Okay? And then I should multiply these probabilities together to get the total probability. I'm actually not multiplying, I'm summing. I'm taking the total because I work with log transformed values. So you know that log transformation converts a product to a sum. There's a funny joke about that. I'll just go. I'll tell that later. Okay. In this case, actually, we can look at independently between the distribution of step lengths and turning angles, because in this model we assume that you randomize them independently of each other. Okay. This is not always the case, but in this case it's such. So here we have the same thing, the probability density of the von Mises distribution given the parameter value that we feed in, evaluated at the turning angles. I take the log of that and I sum. And then I simply sum these together. It's like multiplying all the probability components together. That gives the likelihood of data. Then that's what I return from this function. Okay? So this is an example of how this thing can look in practice in a concrete model. Is that clear? Okay, the joke about the fact that if you do a log transformation, you get from a product to a sum. It's about, you know, why snakes. This is like a mathematical biology thing. If you look at snakes which live in a forest where you have some dead wood in the ground, why they need them to reproduce? Well, it's because adders need logs to multiply. Okay, let's see how the likelihood looks like in practice. And you remember we have 3 parameters in this model. The parameter values, the true values were like 1, 2, and 4. But I work with the log transform parameters. So the log transform parameters, the true values are like 0, 0.7, 1.4. What I'm plotting here is like basically the full conditional likelihood for one of the parameters, for the third parameter, assuming that the 2 other parameters are at their true values. Okay? So this is how log likelihood looks like. It is this curve here. So in the y-axis you have log likelihood, the logarithm of the likelihood. This going from minus 240 to minus 260. And you see that the peak of this distribution is pretty much at the true value of that parameter. So conditional on these 2 other parameters, the maximum likelihood estimate would be around this 1.4, which is the true value. Okay, this is just the likelihood surface. I mean, the likelihood surface in this case is 3-dimensional, but I just illustrate it in 1D by doing this kind of full conditional. If we want to do maximum likelihood estimation, you just maximize this expression, this log likelihood. I mean, if you don't do Bayesian analysis, but maximum likelihood. So here I'm saying that find maximum of this function in terms of these 3 parameters, which I now call P1, P2, and P3. So I'm asking the software, in this case Mathematica, to figure out what are the values of these 3 parameters that give me the highest value of the likelihood function. Okay? It's telling that those values are minus 0.2, so they are like close to the real true values, but of course they are not exactly at the true values because we have a finite amount of data. So there was some stochasticity. So if you would do maximum likelihood estimation, which is an equally valid method, of course, as Bayesian inference, this would be your answer.
So you don't have to define a range where to look for P1 and what step size to look for P1 and P2 and P3 for this maximum likelihood function?
Yeah, you are asking about the details of this find maximum function. Yeah. Like how do you do this in practice inside this find maximum black box? Well, in this case you don't, because this is really nice surface. I mean, the likelihood surface is really something which is unimodal and like, you know, decreasing nicely, so you can, any algorithm will find the maximum. In some cases it's not so easy and then you have to do something else. Okay, then we need the prior and the posterior. Here I defined my prior. So this is the logarithm of the prior density. So I'm just saying that I assume that these log transform parameters, okay? I assume that before seeing the data, they would be like normally distributed with mean 0 and standard deviation 10. Okay? This is just an arbitrary kind of, there is no reasoning why I assume this. but I have to assume something. We can talk about this, like how do you actually set up these priors later, but this is now my choice. This is also something that you can think of pretty uninformative, because this is in the log scale, and you basically say that any values, let's say from -20 to 20 are possible. So it's a huge interval. So here we have the probability density of that normal distribution evaluated at those three parameter values, this log A, log B, log C, and then you sum them together to get the prior likelihood of the entire parameter vector. And then we have the posterior, and as you remember, the posterior is the product of the prior and the likelihood of data, but because we work with log transform, it's a sum of the log likelihood, which I showed in the previous slide, and then this log prior density. Now we can write down the MCMC algorithm. This is now a random walk Metropolis Hastings algorithm with a symmetric proposal. I mean, as said, we could use any algorithm we like, but let's pick this one because this is easy to do and it's really general. And what you see here is that, first of all, I have to have some starting value. I know what the true parameters are, so let's start from that. This is kind of cheating, but let's do it anyway. Let's later worry about that. I just start from the true parameters. Okay, I have here a do loop, which is like a for loop, where index j goes from 1 to 3. Okay, this is my parameter. I'm first updating parameter 1, then 2, then 3. So first A, then B, then C. When I'm updating parameter number j, I start from the old values. I say that the new parameter vector is the old parameter vector, because I do this random walk, Metropolis Hastings. And then I change only one component of that parameter vector, which has 3 values, the jth component of this vector. I add there something with a random draw from a normal distribution, centered at 0, because I want to center at the present value, and with standard deviation 1. The standard deviation of 1 is just an arbitrary choice. I can put any number there. I will soon illustrate what's the influence of that number. Okay. Then I calculate this acceptance ratio, which is the logarithm of the posterior at the new values minus the logarithm of the posterior at the old value. This part where you have this proposal density, that cancels out because my proposal distribution is symmetric. Then I see how big that is, and I accept or not, depending on that probability. So this random with brackets is a random number between 0 and 1 with uniform distribution. If I accept, then I change the parameters to the new parameters. I also count how often I accept. So I add 1 to this acceptance counter. And then I just move on. I do this loop for all the parameters, and then I repeat this, in this case, 1,000 times. Okay? And then I print the acceptance ratios. In this case, they were 0.09 for parameter A, 0.11 for parameter B, 0.16 for parameter C. So most of the times I actually reject it. I didn't accept the new value. And what I did after every iteration round, after I updated all the 3 parameters, is that I appended to the result list the present values of the parameters. Okay? So I can plot how this MCMC chain looks like in terms of the individual parameters. This is parameter 1, parameter 2, parameter 3. The red line is always the true value for that parameter. So you see that they are kind of fluctuating around the true value. It is basically at the stationary state of the chain because I started from the true value. Okay?
Is there any quantitative way to say that it's the range is conserved?
Yeah, there are quantitative ways to look at if you have converge to the true value and how well the chain is mixing. We can talk about those later. I'm not going to do it, but I'm going to show like visually how they look like in good and bad cases. Which is, I mean, even if you use a quantitative way, that's something that you do is to look at these chains. What's the time? I'm afraid I'm going over.
After time, it's 12:40 already.
Should we break for lunch? I still have some slides to go.
Okay, so should we meet here?
I think it takes at least 15 minutes to go to the end.
So you want 15 minutes or 15?
15, yeah.
50? 5-0?
1-5.
1-5 is, so let's continue.
Okay. Okay, so as said, you can plug in here any value you want for this variance of the proposal distribution. So you can kind of propose that you jump very far away, or you can propose that you jump very near to the present value. Okay, let's say that you jump very near to the present value, so that my standard deviation, which was 1, is now only 0.01. Okay, what will happen in that case?
Fluctuation will be smaller, no? Because you jump less.
But the acceptance might change.
Yeah.
Increase.
I think you are kind of all, yeah, you are all, everything you said is true. I'm making smaller steps. So it means that the likelihood doesn't change that much. The likelihood ratio is always close to 1. It means that I'm very likely to accept. Like you see in this case, the acceptance ratios are 0.95 and something like that for all the parameters.
With the true values.
Huh?
Because you started with the true values.
No, even if you start from the wrong values, this would happen. Because you propose small changes, the acceptance ratio is the acceptance probability is the ratio between the likelihood that the new and old values, right. And that's almost 1 because you propose only a small change. Okay. So, great. Now we don't lose much by rejecting all the time. But is this really good?
Wait, I don't understand. If you started from the true values, okay, and you move with small steps, I don't understand how can you accept more than 1/2 of your suggestion.
You are kind of thinking that more than half of the cases you move towards a worse probability.
Worse,
yeah, okay. So if you move towards a better probability, you always accept, because then the acceptance probability is like greater than 1. So it means that you always accept. But if you move towards a worse value, okay, your acceptance probability can still be like 0.99, because the ratio between the new and old probabilities is very close to 1, because it doesn't change much. So, if
I'm unclear about the acceptance.
So, if I'm currently here, like at the maximum, in this value of the parameter, I propose a very small change. I only change here, okay? The likelihood doesn't change much at all. It goes to a worse value, but not much at all. So then the ratio between the new and old likelihood, which is the same as the difference between these log likelihoods, it's almost 0. So then I almost always accept going to a little bit worse value.
But also, if you start with very wrong values,
well, like here,
to the right of the
yeah.
left, and then you increase the variance, then how can you converge? Sorry, when you have a small variance,
yeah.
How can you converge to the true value?
Okay, I think what I'm showing is answering that question in a couple of slides. So, I mean, now we had a high acceptance ratio in this case because we changed only a little bit, but then the kind of the cost of that is that, as I think Or was saying, that you are making only small steps also in this graph. Okay, so this doesn't look very nice. You don't sample the posterior distribution very nicely. So you can call this phenomenon by saying that these chains, they don't mix well, which is the same as this is highly autocorrelated. It takes a lot of iterations to go like from a small value to a high value. Okay, so this is by no way this is optimal.
But when you converge, you won't converge better than the previous?
Well, if I want to, like, this is like something that looks like good mixing, that you are sampling like small and big values like frequently without much autocorrelation. You get the same thing here, but you have to do many more iterations. So if I do like 1 million iterations, and then let's say I thin the chain, I take only 1 out of 1,000, then I get rid of this autocorrelation. So it will give me the stationary state, it will give exactly the right answer, but I have to do more iteration rounds to get that. Okay, let's then do the opposite. Use a large proposal variance. Now it's 2 standard deviation. So this will of course give us a low acceptance ratio, like something like 5% of the cases. Because you try to jump very far, and often you jump to a very bad place. So now the change looks like this.
What was the Y scale in the previous smaller graph? It's the same Y scale between 0.3.
Yeah, it's the same scale because you always get the same distribution. I mean, the result is the same. As I said, the answer is always the same. It was automatic scaling, so I didn't make it the same, but it should be pretty much the same. So what you see here is that there is no autocorrelation, or it's very weak. You can jump from big value to small value immediately. But then you are often staying for very long in one given value. So you are proposing but not accepting many times. Of course you don't want to do this because it takes computational time. So that's why in these random walk metropolis hastings algorithms, an intermediate acceptance ratio is the optimal one. Okay? And you can show theoretically that if you update one parameter in a turn, then something like 0.44 is the optimal value. Okay? So I just adjusted manually this acceptance ratio, this proposal standard deviation to 0.3, which gives me something like that. I mean, not very close to that, like from 0.3 to 0.43, but it doesn't really matter as long as you are far away from 0 and far away from 1.
Why did you say 0.44 and not just 0.75?
Well, you can show theoretically that this is the optimal value if everything is normally distributed. Okay. If you update one parameter at the turn. If you update many parameters in a turn, then like in a block, then something like 0.2 is optimal. But it doesn't really matter, as I said, it's not sensitive to this value as long as you are far away from 0 and 1. Okay, so if I do that, then I mean you look at these, then I would say that these chains are mixing very well. That I'm sampling like the all regions of the posterior quite nicely, even though I do only 1,000 iterations. So typically you need to do more iterations. So this, if you look at these plots like visually, I would say that okay, they mix pretty much as well as they could.
On the parameter number 3, it looks like your estimation is biased a little bit too high, no? It's just because you did few by only 1,000 iteration and not 10,000?
No, I would expect that if I do 10,000, it might look the same. Because it's not so that the posterior mean would always be at the true value. You have a finite amount of data. Mm-hmm. So in 95% times of the times, the true value should be like within 95% interval of this distribution. But it shouldn't be centered around the true value. Okay, then more kind of central concepts. This is that of the joint posterior distribution. So the posterior distribution is not, really for the individual parameters, but it's for the full parameter vector. Okay, this I illustrate here in a kind of a 3D plot, where in the axis I have the parameters A, B, and C. These are now the original parameters. I took the exponentials of what I obtained by sampling. So the distribution of these dots here, these are these 1,000 dots, that's the joint distribution of all the parameters. Then we can look at marginal distributions. So we marginalize some of the parameters out. Like in this case, I'm asking that what is the posterior density of parameters 1 and 2 if I integrate parameter 3 out. Now I get a two-dimensional plot. Sometimes you get like a highly correlated distributions. In this case, these two parameters, 1 and 2, they are not much correlated. So they are kind of almost independent here.
Can you explain again what we're looking at? What is the posterior distribution?
Is this clear what this represents?
Sorry?
Is this one clear? This joint posterior?
Yeah.
This.
Explain it again.
Maybe it's.
The numbers are different.
maybe it's better to go from this side. This is maybe the easiest to understand. This is the so-called marginal posterior distribution of those individual parameters. Parameter 1, A, B, and C. Okay? This is the histogram that you get after you have sampled the posterior. You simply see back transformed. Yeah. So like for these parameters, the true value is here 1, here it's 2, here it's 4. Okay? So this is now the marginal posterior distribution for that parameter. I simply plot the histogram of what I sampled. Okay? But I'm just saying that this is not the full story, because these are like independently of these different parameters. So the full story is given kind of this plot, which are the parameter combinations. Parameter 1, parameter 2, parameter 3. So they all have a value, so you are somewhere in this three-dimensional space. Okay? This is called the joint posterior distribution. But then you can marginalize that.
Each point here is a point from your search?
Yeah, exactly. We have 1,000 points here from this.
Cases or just exception?
All cases. Okay. So it's important that also when you reject, you have to keep that case. So there are some double dots when I rejected. And then you can marginalize that, which means that you integrate one variable out. For example, you forget about the variable 3 and you just look at the projection at the xy plane. Then
but also, if you reject it, what is the meaning of showing this point here? I mean,
what's the point of showing the point twice in this graph? I mean, you don't see it because it's in the same place.
You did not accept it as part of your posterior.
No, it's part of your posterior. You didn't accept the change, which means that this point is twice in your posterior. It has like a weight of 2. It doesn't show up in this graph because the dot is on top of the same dot. But if I, for example, calculate the posterior mean, it has a weight of 2.
But the rejected values are not on the graph, only the step that was rejected. You randomize the values and then you rejected them. So
yeah.
The rejected values are not over there.
Yeah, I mean, it might be that when I go from theta 1 to theta 2, let's say that here the values were like 1, 2, 3. And when I do this step, maybe I rejected the proposal for the first values. It's still 1. Maybe this changed, maybe it's 2.5. And maybe this didn't change, it's 3. Okay? So now this is my theta 2. Okay? It includes some cases where I rejected the proposal, some cases where I didn't.
So the rejected values are not projected.
Yeah, but it's important to, I mean, this is also part of the posterior, although it's there twice. Otherwise you get the wrong result if you don't include them. Okay, so this is what you typically plot, these marginal posterior distributions of the individual parameters, because you can't plot the whole n-dimensional thing. Like this is what I was showing in the butterfly example, like how the movement speed of the females and males look like. It was this histogram, I just plotted the line. Okay. But then you can summarize these into numbers. You can take the posterior mean. You just take the mean of all of those values. It gives you, in this case, 3 values for those 3 parameters. You can take the posterior median, which means that you kind of order all the values from smallest to largest, and then you take the middle one. Again, you get 3 values, which are almost the same because it was pretty much symmetric. Or then you can do your confidence interval, but as said in the Bayesian framework, you don't call that confidence interval, but the credible interval. This is the 95% central credible interval. I order the values, and then I take the 2.5% quantile and 97.5% quantile. Those values are these. Give me those intervals. Like the median estimate for parameter 1 is, parameter A is 1.04, and then this credible interval is from 0.9 to 1.2. And then I can calculate what is the map, which is the maximum of a posterior estimate. This is pretty much the same as the maximal likelihood estimate. But in addition to the likelihood, we also have there the prior likelihood influencing that. I just maximize the full posterior likelihood. It gives me some values. So, I mean, you can use any of these to tell what your results are, but it's important to know what these terms mean.
Usually it's the map,
no? I mean, usually you report like the posterior mean and some intervals, or posterior median and some intervals. The map is not very nice because it's just a point estimate. It doesn't tell you about confidence. Or you do the map and then this confidence interval, credibility interval. But not just the map, because then you don't know about the confidence, which is of course something you want to know about. Okay. Then what happens if you start from a bad initial guess? Okay. So now I pretend that I don't know the true values. I start from -10, -10, -10, which is like a really bad guess in the log scale. Okay. I run the iteration MCMC for 1,000 iterations. And this is what happens. This is the starting value, -10, -10, -10 for the 3 parameters. The true value is shown here with the red line. So this is now the transient phase. You see that you are quite fast, like in 200 iterations, all of these parameters have found like the regime of the true value. What happens after that is that you are just doing this stationary chain. You can't see it too well because the scale is huge. But here you simply see that there is a transient phase and then a stationary state. And in practice you have to separate these. This is called the burn-in phase. Like let's say that if you see that this is happening, let's cut out the first 500 iterations, let's throw them out and assume that the rest is the posterior.
Can you go back to the previous things? 0.3.
Yeah, here I'm using a good proposal density. Of course, now I manually figured out what's a nice value, but then there are adaptive algorithms that you don't need to figure this out manually. Okay, what happens if you generate more data? Instead of 100 data points, you have 1,000 data points. This is kind of pretty clear cut. That in terms of, instead of this likelihood surface which you had before, again shown only for 1 parameter, you have this likelihood surface for 1,000 data points. It looks exactly the same, but it's only because you are far away from the screen. You don't see the axis. So here we go from -220 to -260. Here we go from -2,500 to -2,800. So here we are much more confident about that the value is somewhere here, because like these values are so much lower than those values. Okay. So if you have more data, you have higher confidence on your parameter estimates. What happens if you have less data? Well, kind of a limit of that is that you don't have any data. You only have the starting point. Okay, you don't have any steps. Let's just run the MCMC algorithm. I mean, you can still run it even. Just plug this data in, no data. It's still converging to some stationary state. Okay, we don't have any data, but still we get some estimates of the parameters. Let's plot the histograms of those to see what we got. What did we get? These are my parameter estimates with no data, and exactly as you said, we are getting the priors back. I assume that the prior is normally distributed, mean 0, standard deviation 10. This is what I get back. Okay, this is again kind of a silly example, but it has a meaning because this is something that I think you should always do if you write your MCMC yourself. Try it without data. If you get the priors back, you are happy, probably it's correct. If you don't, you know for certain that there is a bug in the code. Okay, I don't think there is anything really. How far to the end am I? Yeah, maybe it's better to stop here. I still have some stuff about model validation, model selection, but this is enough to understand the exercises for today. So let's stop now here. Thanks.
Thank you.
Right.
Thank you.